Hello everyone, welcome to my channel Chemistry is Fun. Today we will be dealing with the topic hydrides. In that we will deal in detail covalent and interstitial hydrides. Now as we have already seen that hydrides are binary compounds of different elements with the element hydrogen. So the name suggests hydrides. So first we will see today covalent hydrides. The covalent hydrides are some molecular compounds in which some element will have a covalent bond with hydrogen. So since it is covalently bonded, we call them as covalent hydrides. So covalent bonds, as we know, are formed by sharing of electrons. So there will be a covalent bond. These type of hydrides are formed by nonmetals and also by some of the elements like aluminium, tin and the like. Except third group elements, other elements will form some mononuclear hydrides whose general formula can be represented as Mh8-X, where X is the number of electrons which we find in the outermost orbit of the element M. That is the element with which hydride is being formed. Its number of electrons will decide this X factor. Then we do it 8-X to get the formula. So Mh8-X is the general formula of these type of hydrides. In case of boron, we find that the simplest hydride of boron as well as gallium, they are dimeric. For boron it is diboron B2H6 and for gallium it is Ga2H6. So they are dimeric, and in case of aluminium it is polymeric. The molecular hydrides can be classified on the basis of how many electrons and bonds are present in the Lewis structure. In case there is electron deficiency, then we call them as electron deficient molecular hydrides, as we find in the type B2H6 diboron. In this there are less electrons when we write the conventional Lewis structure. The second one comes electron precise molecular hydrides. Electron precise molecular hydrides will be formed by the elements which are there in group 14. These molecules are generally tetrahedral in shape, and example is CH4, methane. Next comes electron rich molecular hydrides, that is excess electrons are there which are present as lone pairs. The examples are ammonia, water. In ammonia we know there will be a lone pair on the nitrogen atom. Now, due to the presence of highly electronegative atoms, they may possess hydrogen bonding also. Next we have to see the preparation of these hydrides. The hydrides are obtained by direct combination of the elements along with hydrogen, otherwise by hydrolysis of some of the compounds of the elements like the borides or silicides, phosphides, sulfides, carbides, etc. Now see direct combination. If you see N2 and 3H2 together gives ammonia. This is a direct combination. In the same way X2 plus H2 gives 2HX. These two are the examples of direct combination. Next we can see that aluminium carbide Al4C3, aluminium carbide, and with water it gives aluminium hydroxide with the formation of CH4, methane. So hydride is formed. Ferrous sulfide FeS with HCl gives ferrous chloride, FeCl2, and H2S is formed. This one. If you take calcium phosphide Ca3P2 with water, it forms calcium hydroxide along with the formation of phosphine PH3. If we take a nitride, magnesium nitride with water, it will form magnesium hydroxide and also ammonia. So we find that either there is a direct combination or hydrolysis of the compounds of the elements which are forming the hydrides. Now if we go to the properties, we find that the hydrogen atoms are covalently bonded to the central atoms, and in these there will be van der Waals forces or sometimes hydrogen bonds. Either of the forces are present. Since these forces are not very strong, they are either gases or liquid or sometimes solid. If it is solid also, it will have a low melting and boiling point. These hydrides are volatile in nature and they have low electrical conductivity. Now if you see the hydrides of the different elements in a particular group, we find that the thermal stability in the group decreases because the electronegativity decreases down the group. For example, in the nitrogen group, if you see as we go from nitrogen towards bismuth, down the group as we go, there is an increase in the size of the atom, so the electronegativity goes on decreasing, and with this the thermal stability of the hydrides of these elements also go on decreasing, which we can see in this list. Now the covalent hydrides, which are having one or more lone pairs of electrons, since they are having lone pairs, they behave as Lewis base. For example, ammonia, you can see there is a lone pair over nitrogen, so it is basic in nature. It's a Lewis base. The hydrides of the 13th group are electron deficient, as we have seen in diboron, so they behave as Lewis acid, as we can see in this equation. Some of the hydrides are also acting as reducing agents, like SiH4 with silver nitrate. We get metallic silver, silicon and nitric acid will be formed. So here we find that hydride SiH4, it is acting as a reducing agent. Because in AgNO3, Ag is in +1 state, whereas in metallic silver, we have seen that oxidation state has been reduced. So this is a reducing action. Now we come to interstitial hydrides. These compounds will be having a transition metal. A transition metal along with hydrogen will form the interstitial hydrides, having the general formula MHX, where X may not be an integer. So then they will be called as non-stoichiometric. We also call them as metallic hydrides, and they are electrically conducting. They are metallic hydrides. They are also called like that because they are electrically conducting in nature. Some of the transition and inner transition metals of the D block also can form black, powdery interstitial hydrides when they react with hydrogen. But we find that metals of the groups 7, 8, 9, they do not form hydrides. And if we go backwards, we see group number 6, only chromium forms the hydrides. So this region is not actually having the tendency to form the hydrides. So this region of the periodic table, that is from group number 6 to 9, is known as the hydride gap because they do not form hydrides. If we see the preparation, these hydrides can be prepared by adsorbing hydrogen, that is on the surface, directly at appropriate temperatures by the respective metals. Some of the examples are YH2, that is yttrium hydride, LaH2 lanthanum hydride. There are also some non-stoichiometric examples. PDH 0.6 to 0.8, this is 0.8. So here we find that this is not an integer, so it is non-stoichiometric. 0.6, that is PDH 0.6 to 0.8. Now if you go for the properties, they are usually black, powdery compounds which are hard in nature and have a metallic luster. They may also possess magnetic properties. They are good conductors of electricity. The density of these hydrides is lower than the metals from which they are being formed. The density is lower because the crystal lattice will expand due to the adsorption of H2. Crystal lattice will expand. That is the reason of this density being lower. They have high thermal conductivity, and if we strongly heat them, they can undergo reversible decomposition so that we get back hydrogen and metal. So when red hot metal and hydrogen, we cool them, we get the interstitial hydride. Upon strong heating, we get metal and hydrogen. So this is a reversible decomposition. Now these metal hydrides can be used as a hydrogen storage media, because whenever required we can retrieve hydrogen, as we have just seen here. They are also used in catalytic reduction and hydrogenation reactions. So I hope that whatever points were discussed today you all could understand. Thanks for watching my video. Please subscribe to my channel. See, all this material which I am providing, it's totally free and you can use it for the preparation of the competitive exams. So please subscribe to my channel. Thank you all very much.